It's pretty cool, actually.
Yeah, they have groups. You can find very weird programming stuff in Google Groups, man. Very, very weird. Okay, so let's go as fast as possible because maybe I don't want to. I want to see if the programs will work, man. Okay, so let's pick an example. I think this example is the best example. So this is what an assembly file of Chime will look like. And the syntax is pretty simple actually. So when you have a column in the beginning of the line, that means that you're defining a label. And then it can be a label of two natures. So the first one is a label of I'm gonna call it a function label. So means that we're defining like a main label, and we have instructions here, and we have four instructions in this case. And you may ask, okay, we need to have six. What happens if you have less? That means that you're gonna have zeros fulfilling the empty space, which is fine because zeros are conveniently chose to be the fetch instruction. If you have more than
I would say
six,
intelligently chosen,
yeah,
not
that's very
conveniently.
very clever. That was very clever from the paper. If you have more than six, we should throw an error, which I actually forgot to do in my implementation. But that's like one throw. That's very easy. Uh, That's the first kind of column labels. The second is when you're defining a variable. So you have a column, then a name, and this is a variable because this is a number. So the hashtag means that this is a literal. And for this program, we also need to talk about the star. So this is a dereference. So you're actually when you're using this, you're saying pick the value of this label. So in this case, 34. And because the instructions are put the literal, and then do a plus and then stop, that means that you're gonna sum 34 with 35, and we should have 69 at the end. And I'm gonna actually demonstrate that. So how the heck did I make this? So just build. Okay. Then you do chime. Then you do the program. So samples sum. And then you need to pass your dialect, which was a very unexpected feature that I implemented by accident. And here you have it, 69. So now let's go to the parsing of how this
I
can
wonder
come.
why that number in specific.
Oh, because this is a meme number, such as 420. 69 is a meme number as well. I discovered today that apparently 1337 is also a meme.
That's because it's the elite number.
Okay. So I should go through the code. So
Leets, you
everything's
mean like friends leets?
Marinho.
Friends list? I don't know.
We can
And
talk about
elite.
that later, but I just use
Maybe
it.
later.
Then it could be a whatever number.
I
Um,
like I like to use 413 and 612 because Homestuck basically.
mm. Okay, so how do we do this? So this is the function that does it all. So you call this when you want to parse. So this is actually what the VM is calling. When you ask to execute, you pass as parameters the file path and the keywords path. And then there's a bunch of Objective-C stuff going around to read a file. We spent like 1 hour discovering how to make this happen the first time. Then there's a very convenient method for strings, which is component separated by string. Then we prepare the accumulators basically, because this is basically a fold if you think about it. So we have labels, variables, and keywords. That's okay. So the keywords we are actually doing something else, which is we call load keywords. So what does this do? This is basically reading the keywords file, separating by new lines, and
Hmm.
it's going to the opcodes enum and mapping each key, each word in each line separated by new lines in the keywords file, and mapping that to each opcode that we have available. That means that it's going through this, and it's saying, okay, this symbol will be correspondent to this opcode. And it's doing that until the end because I'm using the opt total. So that's how I managed to create the dialects feature, because it's basically a matter of swapping this file and you can change whatever. So I created mine. I tested with emojis and it worked.
So we use Unicode.
Yes, it works
Incredible.
with Unicode, which is pretty cool. So then after you have the keywords, now we know how to read the assembly, because now we are presuming that the assembly that was passed to us, it is using the keywords from the file that we just loaded. And we're going to fulfill the labels and the variables. The labels are basically the function labels that I was explaining, and the variables will be the variable labels. So the way that we structured this, Marinho and myself, we did this a two-pass parser. A two-pass parser. The first pass of the parser will collect the labels. That's its whole intent. So if you go to the pass one, which is this function here, you're gonna grab all the program is separated by new lines again. So this program right here, we had each one of these lines in our program enumerator. And then we check if this is a label line, the current line of the loop. How do we check that? We created a bunch of auxiliary functions. So isLabelLine is basically asking if the string starts with column and stuff like that. And then we're gonna pop the first char because we're gonna remove the column, because the label is everything, is the first token separated by spaces of the line, removing the column, right? Then we're gonna ask if this is already saved, and if it is, we're gonna throw an error. Why? Because this means that you have something like this, right? And then you can have blah 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 here. If you pick main and go to the map of labels and you try to find it there and it is already there, that means that this very clever programmer is using our assembly to do shadowing, and we're not going to allow that. Then we're going to throw an error. If the thing is not there, that means that this is a new label that we just encountered, which is cool. Then we're going to verify if this is a variable label. So the variable label is this one. So how do we check for that? We check if the next token separated by spaces is a number. So if you check for isVariable, I can actually do this now because I have LSP. It's basically grabbing the line, grabbing the second token in that line, and checking if it starts with hashtag. And that's it. If it is a variable line, we're basically gonna remove the hashtag from the number, and you're gonna save in the variables map. We're gonna save that variable. Otherwise, that means that this label line, because we are in this if still, this means that this is a function label. So we're just gonna save it. And it's without the column, again, without the column. And that's it for first pass, basically. Questions?
Counter.
Yeah, the counter is just for error messages, by the way. This is a counter so we can tell you which lines are conflicting. Because when you're doing parsing this simple, it's so easy to make good error messages. It's incredible.
Right, and the line number also corresponds to the memory location, except are we dealing with like how are we dealing with the fact that a programmer may decide that, oh, I need this memory address like to be an actual memory address initialized to an integer? How does that work?
I don't think this is possible currently. We're gonna have to implement that.
Because like right now, if you want to say, okay, this memory address, I'm setting it aside to be a variable, it has this name, and I want it to start with this value. we can't really do that conveniently because like if we try to do label integer, it's going to think it's meant to be like a compile time variable, right? Which
No, wait, you said
is
something that I
not
think we can do. You said
what
that you
you
want to tell
want.
that this variable starts with this number. Is that what you want?
No, what I mean is I want to be able to say, okay, this memory address right here will have the value 34 as its initial value.
Yeah.
I'm gonna call it first number, and I want to be able to like refer to it as a pointer because I intend to use this particular memory location as a variable,
Oh,
like
the
at
memory
runtime.
location 34.
No, no, not the memory location 34. The memory location, whatever line number that happens to be.
Oh, I see, I see. Yeah, this is not implemented. This is not implemented. Although we kind of could do that if we manage to make this happen.
Yeah, that's like the original intent, except like you mentioned being able to do compile time variables, and I was like, yeah, that's actually convenient because sometimes we just want to say, look, there's this magic number that I'm gonna use everywhere. I don't need it to be stored in memory, but I want to give it a name. So
Yeah,
what you did is basically that, which is convenient in its own right,
yeah.
but it you don't have the option to do it the other way, which is I actually want this to be a variable at runtime, and I want to be able to mutate it and refer to it by address.
Yeah, 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 that's true, that's true, that's true.
Uh,
Oh well.
also, uh, also the way it's parsing right now, I'm assuming that um, you are not discarding the lines that are being used as variables at compile time, right?
No, I'm not discarding.
Which means that when we compile the program, we have some extra zeros in the program image, essentially, right? Of the lines that were used to write the variables in the original assembly.
Yeah, 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 that's also true. That's also true. Although we could optimize that when we go to compilation, like that's gonna be a whole separate topic. Uh, but I think I understood your point. When we decided to make compile time variables, we basically make it difficult to use the approach of just referencing like runtime things. That makes sense. That makes sense. Okay. Let us continue with the second pass. So what is the second pass supposed to do? It's going to read the program again, but every time it encounters a label, a function label, it's going to ignore that, and it needs to pack these instructions. Oops. These instructions here, it needs to pack that into a 32-bit word, right? So how do we manage to do that? So what we are doing,
Nathan is gone.
we are basically iterating through the program again, the same approach as before. The first thing that we need to check if this is an empty line, because if it is an empty line, we're just gonna pass through it, right? So, and this is important because in the beginning I was in the mood of trying to remove the empty lines, but then I understood that if I did that, the addresses, because they are relative, they would break. The relatives to the entirety of the program, counting new lines. So I decided to not remove them. I just decided to jump them. And I could remove them if I remove them in the pass one, right? Because in the pass one we would have saved the locations of the labels, already filtering empty lines, but I decided to not do that. Um, so the first thing that we do is to check if this is a label line. So if it is a label line actually, we're gonna check if it's not a variable line, right? So again, there's a chance that we are reading this, and there is a chance we are reading this, okay? So if we are not reading this, if we are not reading, oops, if we're not reading this, that means that we have to pack stuff, right? Because that means that we have instructions to put in a 32-bit pack. So what I do is basically I separate the things by spaces. So I have now an array of all the instructions. I pop the first token because this is basically the label that we're going to ignore, right? And then I pass the instructions to a function that I created called pack forward. Pack forward. And of course it's going to the header of freaking course.
Real
Uh,
quick, I just had an idea, and it may be a stupid idea, but it's an idea nonetheless. Um, like we know program starts executing from address 0, right?
yeah.
What if, um, hear me out. Um, what if we had a modal reader for the parser where we say, okay, this line is labeled main, this is address 0. Everything before that is a compile time constant, so or a variable or however you want to call it. Everything after that is just the the textual representation of our memory image, which means in our use case, if you want to differentiate like um, a value that we're just using as a magic number at compile time versus an actual runtime memory location that we just happen to initialize to an integer, we can tell those apart because one of them will be before main and the other will be after main.
Yeah, for compile time area and runtime area. Okay, okay, that's interesting. That's interesting. Although I don't want to do this today because today I really want to focus to see if we can run the programs and explain how the
No,
parsing works.
that's fair. It's just I just had the idea and I wanted to throw it out there before I forget it.
Yeah, that's fair. That's totally fair. So after I pack and how do I pack? This is basically doing exactly as we did before with pack word, but this is a full word because this is gonna always have 6 mem opcodes, and if you have less than 6, we're gonna fulfill the empty spaces with 0. So that's the only difference actually. And then we're gonna add that to our mutable array of bytecodes. If else, so if we are not in a label line, that means that we are executing something else. So what are the options of the something else's, right? It can be a literal, so it can be this, right? It can be a dereference, and it can be a variable, I believe.
It should be able to be like an
Oh,
address,
an
like
address, an address. So there's
an
also the
address, an
chance
address,
of
yeah.
being this, right? So being something like this, right? So how do we manage all of that? So the first case is if we encounter a number. So how do we check if we have a number? Very easy. We just check if the line starts with a hashtag. If the thing starts with a hashtag, that means that we have a number, and what we do with this number? We grab the number, and we just add it to our bytecodes, converting it to a new int32. That's basically it. If we have an address, right? So how do we check if we have an address? Very simple. We just check if it starts with ampersand, the line. Um, Kind of crazy, right? We just fixed a bug because Racket Tower was depending on new lines, and the entire parsing of this is depending on new lines. Anyway,
Yeah, but in this case it's fine because the input file is text to begin with.
yeah, I agree, but it's kind of funny anyway. Okay, so if we have an address line, um, if we have an address line, we're gonna see if we have the location of that label, right? Because when you use an ampersand, you're basically saying, give me the address of this label. That's what you want. We search if we have that available. If we don't, we say that we don't have that available. If we do, we grab it and just add to our bytecodes. That's it. And finally, we have the is the ref line, which is basically these
Yeah.
things.
If it starts with an asterisk, that means it's a name for our magical number that doesn't exist at runtime, but we gave it a name because we
Yeah.
use it in multiple places, and that's
And the
convenient.
boilerplate is kind of similar. So this if and else is basically the same, just the error message that is different. So this is one of the things that I want to attempt to factor out. But it's basically the same. If we but and the map is different, right? Here we are searching in the labels map, and here we're searching the variables map. And that's pretty much it. And else, that means that you're using an illegal uh, instruction, illegal something. So I just say invalid line encountered, and I just say where it is. And we also have the counter because we want fancy, useful messages. I'm not gonna say fancy. I'm gonna say useful.
And what if we have an empty line? How
We
are we
just jump
dealing
them.
with that? Okay.
We just
But
jump them.
then, isn't that a bit of a problem because we use the total line number, including the empty lines, to decide the addresses
No,
in
but
the
that's what I
first
said.
pass?
If we don't want to remove, if we don't want to depend on the empty lines, that's fine. But we need to filter them throughout the pass one first, because the
Okay.
pass one needs to be to have the line numbers correct. So
Uh, but actually, that's the thing. Like, if we don't filter the empty lines in one pass, but filter in the other, they will be out of sync when we build our binary image.
yeah, that's what I said, basically.
Yeah.
So if we want to do with one, we can. We just need to do with the other one as well, which I didn't because I was very satisfied with this because it took me a while to see which thing to cast to what. Uh, it took me a while to get this done, but it managed to work. And I tested two programs, right? I tested the sum, which is this program, and as we saw, it gave us 69. And this is actually the logging as well. So PC fetch, fetch literal plus and halting. And then the halting conveniently also does a peak on the top of the data stack, which is very convenient.
Um, Traditionally, forms have a dedicated, like, built-in function for that, which is something we can look to implement once we have syscalls, I think.
Yep, yep, yep.
That day will be glorious.
When we have syscalls, we are gonna be very, very close to like, oh man,
Yeah.
this
When
is
we
getting a lot serious.
when we have syscalls, it's basically a very primitive form with little to no metaprogramming.
That's true. That's true. I also checked the equality program, which is this one, and it works. So let me try to explain to Mageta how this program works, and Marim can correct me if I get something wrong. Okay. So what is this program supposed to do? This program is supposed to do the following, Mageta. It's supposed to put in the data stack these two numbers, and it's supposed to call this function. Okay. And then this function will do an XOR on the two numbers, which as far as I can tell will always be zero. Will always be zero. Because they are the same number. And then we're gonna do a jump zero, which is an instruction that only jumps to the label if the top of the stack is zero. And if that's true, we're gonna jump to true, which is basically gonna pick the -1, put in the data stack and return. So it's gonna return to here, right? It's gonna return to here. We're
Wait,
gonna
so
go.
wait. So equal returns zero if it's
Yes,
equal.
yes, yes,
That's the thing. We XOR. If the numbers are equal, we will have a zero on the top, which means we
Yeah.
will perform the jump to true.
yes, yes. If the top of the data stack is zero, we're gonna perform the jump. This is a conditional jump. But instead of
Yeah.
using the registers as in x86, we're gonna use the top of the stack.
And because this is a jump, when we go to true and return, we don't return to equal, we return all the way to main, actually.
Oh, that's true actually. This is not a call, this is a jump, so I said it wrong. So this we ignore this zero here. We're gonna have the -1 on top of the data stack, okay? We're gonna have -1. And let me explain why we're not going to return to here. Because the difference between a call and a jump zero is that a jump zero doesn't put the return address in the return address stack. Okay? That means that this is once you jump, you are done with this piece of code. You need to come back to here somehow, but you can't do that using return. Okay?
Actually, that's the thing with the jump zero. If you don't jump, you just continue executing the rest of the
Yeah,
equal
yeah, yeah. But in
function
this
as if,
particular case, we will jump.
hey, we will. Um,
Yeah,
we could change the one of those numbers to be
and we will do
different, and
that
then
also.
yeah.
We will do. I just want to see if Magetta understood the mental process that the result of this program will be -1.
And by the way, the reason it's -1 is because of choose complement. -1 is represented as the word with all bits set, so it's the truest possible value.
Yeah, which is a ginormous value as we are about to see. But I want to see if Magetta is following us.
Yeah.
Okay, so the return of this program, given these two numbers, is going to be -1, which, as far as my calculation goes, means the the 32-bit number in length with all ones. And as far as I can tell, this number is uh, okay. So I don't
Oh,
know
I
what.
think the dialect you're using has a different name for XOR.
I also think that. I also think that, and that's actually a pro. Maybe I should change. I should add comment support to this thing because now we need to go to the op codes and see which position is the op XOR. So it's on top of the plus. Okay, so it's just adding XOR here. What else? Jump zero. I also. Oh, I don't have the the dash and the return. And there we go. I think this is the 32-bit in length with ones. I think that's the one. I really think so. Then, in order to test if the other branch is working, we just change this number, and it's not working. Did I save? So we have a bug already.
Oh,
We do have a bug. So what it was supposed to happen? If this XOR would not be true, right? Will not goes to zero, I should say. It will go to something different than zero, which means that the jump zero will not do anything, which means that you're gonna put the zero in on top of the data stack, and then we're gonna
and then
return
return.
to whatever
Yeah.
we call it,
Hmm.
and then we're gonna halt after that, which means that this zero should be on top of the data stack, which means that this is wrong. That's what it means. So that's actually a thing. So
Did you actually save the file after you changed the number?
yeah, I saved the file.
Okay. Yeah, that's concerning.
Yeah, so something in the jumps. Yeah, so this is definitely wrong. I'm really also concerned, now that I think about it. We are not saying jumping ever, even when we were doing the one that should jump. So, yeah, we're not saying jump anywhere, which is concerning. So, jump zero. Jump zero. Okay, so it's not here that we do that. It is in here actually. So, jump zero. Yes. We're not performing a jump zero because this should print jump zero.
Yeah.
Maybe the order of the opcode names is wrong in the dialect.
The order of the opcodes is wrong. Let's check. So let's check that. I
And
should actually put
Oh,
fetch here.
so the words there they should map exactly the
Yeah,
corresponds.
yeah, exactly. And if we add comment support, we could do something like op pc fetch here, so we don't have to do the mapping
Mm-hmm.
by with our heads. But the jump zero is definitely correct. It's definitely the third one.
okay. That means that maybe the implementation is wrong.
which is what we are here to fix. I'm just checking if the other ones, I didn't miss any of them, because again, we don't have a program that tests all of them, so we can't be certain if first if they are implemented correctly and if we have all the words here, right? So load R, load store R, load A plus, store A plus, load R plus, literal, and not or
I'm pretty sure these sample programs I wrote use the word not, like the actual words not and ands and all X or the
okay, so you're
opcodes.
saying this and this.
And
Well,
I
I
don't
can fix the rest. I
recall.
can fix the rest later. Plus double, half plus a star. Nope. And there's one that
And
we are
there is
missing, which we don't care because this is only for implementation details anyway. Okay, so it's definitely a problem in the. That's actually the problem that I want to talk to Marinho how to fix. I don't know how we debug the parser because the parser spits bytes codes. And how the heck we fix that? How do we know if something's
Doesn't Clang
correct?
have a debugger?
Doesn't what?
Clang, I think it has a debugger.
It has a debugger, but like, how are we gonna debug that? Even with the debugger?
Emacs has
we
a thing to debug, or you can try VS Code.
No, I
I
mean,
mean, what I mean is like just attaching when you read and trying to read the string of the things you read. At least that. Maybe it's
there's
just
also
misreading the things.
there's also the crazy option if you want.
what is the crazy option?
Well, we have an assembler. We can write a disassembler.
Wait. No, 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 no. But that's what I thought you would say, but I was hoping not.
I
Uh,
told you it was the crazy option for a reason, you know.
yeah. Okay, I actually there is actually a better way, which is to just log whatever we are about to push. So let's put something like I don't know. Uh, let's put this in the beginning first. Let's see what the heck happens. So opcode. I'm pretty sure this is actually LU or maybe LLU. We're gonna
Not
see.
no, no, it's just W.
Okay, so just build. It should be fine. Um, okay,
Oh,
okay. So this is actually a little bit useful because now we can try to understand which instructions are we putting in, and that's very very useful. So let's put like this, and let's add the program equality. Okay, okay. So the first thing that we put is a 20. That's a 20. Uh, which is weird. 20 is literal. I think 20 is literal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. No, it's not literal. Am I counting wrong?
20. No, I think you counted right. Do the following. Go expand that buffer. Not expand. You don't need to expand. Yeah, just go all the way down. Just
All the
want
way
to see
down.
that. There are three no, three lines on the bottom. So go to the
Yeah,
literal.
let's remove the comments though.
No, no, no. I would say you don't need to do. I
Okay.
just go to literal. I think
Mhm.
it's Control C and then you release the control and then L.
Control
No, sorry,
C,
Control X, release the control. Yeah, Control X, release the control,
Control
and then
X,
L.
release the control. L.
L. So there are 16 lines minus 3 on the bottom.
So
So
it's
that's the
46
position.
minus. Wait, I'm confused. 45 minus 3. What does that
So there
mean?
are I think it should go up, right? So 30 lines less, how many? Uh, one, two of the comments. Eliminate the comments. So one, two.
So it's
Go up.
4.
Yes.
4.
No, no, go up. Yes. Two, three. 4, 5, 6, 7, 8, 9. So less 9. So 30 plus 9 nines. So 21.
I think this is gonna be a lot faster if I just do the Ooga Booga way, man.
Well, yes. And it will be easier to debug in the future.
Yeah. So yeah, I thought about doing a disassembler as well, but then I said, man, that's gonna be a lot of work. Oh well, not a lot. Maybe we can do it like in an afternoon, but it still work. And I thought maybe, just maybe, we implemented things correctly. I guess not. I guess not. Um, I think this is a 20. Yeah. Okay, this is a 20. So that's great. That's actually great. Uh, 20, 20. Then a call, which should be 4. Yes. Then then a
And a
halt.
halt. Yeah.
And by the way, this is just the program, right? We don't have the access through the parser with the data stack and stuff like that. So that's something that we need to be aware of. So after we have the 4 and the 6, what should we do? We have a 24. So what in the heck is a 24? Uh,
The XOR.
the XOR, which is correct, right?
Yeah.
Which is correct. Then we have a 2, which is jump 0. Then we have a literal again, which is 20. Then we have a return, which is 5. And that's the end of the program. No, it's not, which is 5. Then we have another literal and then another return, and that's it. So my understanding is that this needs to be an execution problem, not a parsing problem.
Yeah, the parser looks to be correct given
Mm-hmm.
the opcode numbers.
Yeah. And
The
this is
not, I don't think we actually care about the not, do we?
I'm gonna number all of them anyway. Okay, so now we need to go to execution. We definitely know that execution is wrong because you don't see a print in the jumping, and we already checked that the parsing is on the problem, so it needs to be the execution, which is surprising to say the least. So let's start from here. Uh, okay, so wait, the opcodes are correct, and we
Oh,
are
I
not
think I see
going
the.
go.
No, wait.
Okay,
No,
because
I was reading it wrong. Yeah.
look at here, we the log is not within the method, which was my bet. It's actually here. So we are never getting to this if. I think this needs to mean that the fetching of the instructions is wrong. And
Hmm.
that's where the disassembler would help us, because now we need to understand how to have 32, like 6 instructions in a single 32-bit word, which is not as easy. Definitely not as easy. Definitely not as easy. So let's think about that. I think there's no way around it. It needs to be this money.
Select next instruction.
Yeah, this needs to be wrong. I don't know how, but it needs to. Kinda needs to be wrong. Well, in the beginning, this will be empty, right? The ISR register. This will be empty,
Zeros. All zeros. Yeah.
all zeros, which means that we're gonna execute the fetch, right?
Yeah.
So is this the PC? Yeah, this is the PC fetch, right?
It's the PC fetch,
Which we
indeed.
are doing. Which what we are doing. Uh, Actually, we can jump some of the correct ones. So the PC fetch is definitely the one that always starts any program. The 220 is gonna be the fetch literals, right?
They
The
and they work. We know already from the previous program that they work.
Yes. The 4 is the calling. The 4 is the calling, so we are good until here. And then we have 3 PC fetches in a row. which is kind of
Yeah,
sus.
that's actually that's not actually right. We should have a single fetch to fetch the first word of the function that we're calling, and then we should start seeing XOR and whatever.
Yeah. So my understanding is that the calling is wrong. My understanding is that the calling is wrong. So let's go to the calling. So calling, call. Okay.
Value of PC.
So what we should be doing in the instruction in the operation call, we are first checking if we have PC in the registers. If we don't, we just say that we have a problem.
I'm more hardware.
Yeah. If we do have PC, we grab the value of PC. We grab the value of PC. We put in the return stack the value of PC plus one, right? So this is basically the return address after you do a return. Um, we put in the PC the value of the RAM at the position of the value of the PC. So this is basically
Yes.
doing the jump. So this is basically doing the jump. And then we push into the instruction stack uh, the contents of ISR, and
And then we
then we
reset
set
the
ISR to
address
zero.
to 0.
Wait,
Yeah,
we set
maybe
ISR to
the
zero.
yes, so that when we finish executing the call, the PC is now pointing to the address of the function, and ISR is 0, which means we fetch the first word of the function so we can
But how are we
execute it.
doing three PC fetches? We should be doing only one, right?
Indeed, we should.
But we are definitely doing three. We're definitely doing
We
three.
are
I don't know how
definitely
that's
doing 3.
possible. Hmm. How is it is possible that we are having three PC fetches? What does that mean?
It means that it fetches a 0, and then we execute the next word, which also has a PC fetch because it's a 0, and then we execute the next word, which means that actually we're emitting the wrong address that we're calling.
That's a possibility, and I have the logs commented out, so we can actually uncomment them. So ns log, yeah, these ones, yeah, these ones.
Real quick, go back to the loop that emits the words, like the second pass. Go to the second pass,
Back
please.
full.
Right. So if the line is not empty, we
Check if it's a label line first.
yes, but if it is empty,
We do nothing.
we
This
do
iteration of the
nothing.
loop will do precisely nothing, aside from incrementing the counter, of course.
That's not correct. We should at least push a 0, or when we collect the addresses, we should skip the empty lines as well when we count.
I'm very confused. Why, if we have an empty line, we should push zeros? That doesn't make sense to me.
Because like the original idea for the very simple two-pass assembler is that each line corresponds to a memory location.
Oh, we are actually chopping off memory by not adding zeros to them.
Yes.
So what you're saying is that in this else here, we should actually put um,
No, in
something
the if
along these lines here.
no if the line yeah if the line is empty, we should do something like that basically. Just push a
Zero.
0.
Man, looking at this, I'm really tired of parsing.
It's
The
I
200
feel
other
like
lines, Magit.
when you started, you opened this code and I lost all my energy.
But it's
the
so
other
easy comparison
option,
to whatever we have done, man.
Yeah, it is easy, but that's not the point.
Lemos, the other option is
We're going
instead
to.
of pushing instead of pushing a 0 when we hit an empty line, is we go to pass 1 instead, and then we maintain 2 counters instead of 1. One of them contains the total number of lines, like actual lines in the that we're reading. The other one contains the same number, except it doesn't count the empty lines. And that second number, without the empty lines, is what we use for the memory locations. This way you can have a more compact binary, and still have accurate line numbers for debugging.
Okay, so real line counter. I think that's easy enough to implement right now. And then NSU integer non-empty lines counter,
Also 0.
also
And
0.
then
And then in the
whenever we
beginning of the program, we're gonna check if something is empty. So is line empty. Oh, I forgot the shortcut. Magetta, help me.
With shortcut.
The shortcuts to identify to put the arguments in the when you do autocompletion.
Tab.
you're
Okay,
missing a close you're missing a close parent there
I
before
am missing a
the
close
bracket.
parenthesis. So if the line is empty, we are just incrementing real line counter. Actually, we're gonna do this anyway, so it's much better to just do not. Uh, this if here oops, we just add it like so. And for the error messages, we're just gonna say real line counter, and that's it. But for the labels, we're gonna do only the non-empty,
I'll be right back, by the way.
uh, non-empty lines counter. Yeah. So um, we always gonna be incrementing the real lines one. And I think I should be
But
consistent. So real lines and real lines. Yes. So we always put the real lines plus plus, but this one needs to be here, and this is going to be the non-empty lines counter.
yes.
Is that what you're talking about?
Yeah, and then we go to the second pass and turn it back to how it was without.
So you're basically saying to remove this.
Yeah, that's the second option, which is probably better because it results in a more compact binary.
Yeah.
And yeah,
Okay, I have no idea if this is going to work first try. Let's see. Okay, so let's actually go to sum. 69. 60
it
fucking 9.
works. It works.
Let's now go to equality. Equality. We have a jumping 0 there, which is promising. I'm gonna go to utilities and just comment this out, and I'm also gonna go to the ns logs. Yeah, these ones that are happening here, and I'm gonna do it like that, and then we're gonna just build Chime. Actually, it's a lot easier to just build this. Okay, which version of the program are we using? Okay, we're using the one that should result in -1. So this is supposedly, allegedly correct,
This is
right?
allegedly correct. And in
Yeah,
fact, you can see that it's executing the jumping 0 now.
yeah, it is executing the jumping 0.
And the XOR before that. So
Yeah.
XOR jump 0 fetch, which tells us that we did jump, actually.
Shut up! It worked. Okay, so the problem that I did is that I forgot that each line is actually a memory cell, which means that if we have an empty line, that should be a 0. That was my bad. That was my bad. Okay. Okay, I learned something, definitely. Okay, so next program. Print. But this is the original Magetta thing, so we need to transform that to syntax and blah blah blah. Let's go to this one.
Abstraction.
Let's go to this one. So what should this program do? So we first start by putting 1025 in the data stack, and then we do a call. That seems sus.
We're missing a second literal there.
Yes, yes. So now it seems to be correct. Then we're going to go to the minus. The minus we'll call negation, and which means that I need to change my, oops, I need to change my dialect. So keywords. So
Why?
wait,
No,
minus?
negate is actually a symbol. You see, there's a label before that.
No, 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 yes, but I just noticed that we do have I already changed the not here, so it's all cool. Okay, so we're gonna pick the 1025 and this 1612. Well, all of those are in the data stack. When you call the
When we,
minus, sorry?
yeah, when you call the minus, we call negate first,
Yes, we call negate first, that's true. Which
which is
basically means, which
numerical negation. It's numerical negation.
it's numerical negation. So you're basically changing these to minus 612, I think. Oh no, this
Yeah,
is a
not
binary
is
not. So this is actually changing to something that I have no idea.
yeah. Fun fact: if you have binary not and you have increment, then you can implement arithmetic negation by
Well,
just
with
composing them.
choose complement, I'm aware of that.
Just complement, yeah,
Okay, so you're basically implementing two complements here because you are doing this and then adding a 1. So this is two complements for sure.
yeah.
So this is basically
So
transforming this to a negative number, and then you do a return, which means that you're going to do a plus with the 1025, which effectively means that we should have the subtraction between 1025 to with 612.
and 12, indeed. And then the return value of that we expect to be 413.
Okay, so let's go to the program and say that we want
Subtraction.
subtraction. Okay, so you're actually using plus like this.
Um, and there we go. There we go.
It
413.
works! Can't believe it, man. It works. So cool to see it works. Okay, next one. So we have equality already. We have subtraction, sum, variable, and triangle numbers. So what the heck variable does? I'm very curious about that. Mm,
That's a fun one.
okay.
That's a very fun one.
Okay.
But it is actually not gonna quite work because um,
Oh,
I
because
I
you are using
assume,
the address for the compile time variable there.
yeah, I'm actually saying no. This is actually a memory cell. The initial value is 1, and the address I'm going to refer to as the thing. So it's not actually a compile time constant. It's actually a real memory address at runtime that
Yeah,
I
but that's
expect
not
that
how
to
the
be.
parser understands this. That's not how
Yeah,
the parser understands
yeah,
this.
the current parser is not gonna be able to do this program quite yet. But the basic idea is I do a bunch of loads and stores on those addresses, basically.
Okay, but what about triangle numbers? Can we execute triangle numbers?
I think we should be able to. It doesn't use. Yeah, we can. We totally can.
Okay, so
This
I have no context of what this should do. Let me try. Let me try before you say it. So we are putting 5 in the data stack and then we are jumping to triangle. When going to triangle, we put 0 in the data stack and then we just jump without condition to triangle loop. The triangle loop does an over, which I already forgot what it does.
it copies the second item from the top of the data stack onto the top of the data stack. So like,
Okay, so the 5.
the, yeah, it's gonna copy the 5 on top of the 0.
So it's going to be
So the
5
stack will be,
zeros 5. So this
yes.
jump will not go. Another over. So now we are putting the 0 on top of that.
No, because the jump 0 will drop the value at the top of the stack
Oh,
after
the
it
jump
checks
0
it.
not only inspects but also drops.
Yes.
Okay.
Because like if we know, like yeah, basically it says, oh, I'm using the top item of the stack, so it will be removed. If it's 0, we jump. Otherwise, we do nothing.
Okay.
But the drop is an unconditional. It always happens.
Okay. So then we're going to remove the 5. So now we have 0, 5. Then we do an over, which is basically means putting the 5 on top again. Then we do a plus, so it's going to be 5 plus 0, which is equal 5. So we have 5, 5. Push R. Push R is going to pick the top of the data stack and put in the R register.
Yes. So the 5 that was
This,
on the top after we added up the 0 and 5 will now
yeah,
be on the return stack temporarily because we want to operate deeper in the stack.
yeah. So we are putting in the return address, return stack, the second 5 because we also have another 5 in there.
Yes,
Then we have another literal, which basically
which
means
is
putting a
minus 1.
-1. So we'll have -1 and 5 in the data stack and 5 in the return stack. Then we pick the address of triangle end.
Wait, did you guys fix the other?
No, actually you're going to skip those
Yes,
two values
we did
because
fix. So let me get this just for a moment, Marin. So right now we have equality working, we have sum working, and we also have subtraction working.
What was the problem with the quality?
The problem was that I forgot during the parsing that every single empty line in our program is an empty cell in memory. So basically, our assembly is actually mimicking memory itself. So if you
Okay.
have an empty line, this is actually saying to the VM that this is a 0.
Mm-hmm.
yeah, so Lemos and I, we just changed that real quick to if there's an empty line, we just ignore it. We pretend that empty line wasn't there.
Yeah. Okay.
So to that
Okay.
effect, the first pass, the one that collects the addresses,
I, I can show you that.
it has to keep two variables now. One of no name, one of real lines
The error messages.
for messages, and one that only counts non-empty lines, so we don't fill up our memory with zeros just because we decided to put some spacing in our program.
Yeah, yeah,
Mm-hmm.
yeah. So basically, we just adjusted that, and the subtraction immediately worked, and the equality also. We cannot run this program because this program is using the trick that Marinho talked about in the beginning of using the variable definition as an actual label, random label. So you want to use its address, but that's not possible because I changed this to compile time variables. So we're gonna have to do something about that in order to run this program. But he told me that we can run
Um,
this one.
my first instinct, real quick, just going back to the compile time variables thing, my first instinct is to say, okay, if you want to compile time variables, sure you can do that, but you have to be explicit. Instead of using a colon, we use a different prefix symbol for that, and that's the end of that, basically.
Oh yeah,
That's
we
the
can
other
just
option.
swap that, right?
Yeah, if we just change the colon to
Symbol.
another symbol, we wouldn't have to mess around with, what do I say?
Okay,
We
I
wouldn't have
want
to
to
mess
make it
around
like
with.
this. These are the compile time variables, and these are just normal
That.
labels.
Yeah, and then the path that actually emits the code will treat the lines that are compile time variables as empty lines, and
Yeah,
then that should be it
yeah.
basically.
Then we can get back to the jumping and running this program. But in the meantime, we are executing this program. We're in the middle of executing this program, Magita. So I'm gonna backtrack a little bit so you can follow us as well. Uh, if you are tired, I remember grabbing a piece of paper because you're gonna have to control the stacks.
And there are two of them, so make sure
Yeah.
to keep track of both.
So the first thing that we do in this program is to put the 5 on top of the stack, and then we call triangle.
Mm-hmm.
Uh, then we call triangle label, right? So this is a calling, a function call. Then we put a 0 on top of the data stack. So again, we have 5 on the bottom and 0 on the top. Then we do an unconditional jump to triangle loop. And triangle loop does a bunch of operations. The first one is an over. What is an over? It picks the second element from top to bottom and puts a copy of the second element on top of the stack. So right now we have 0, 5, right? After the over, we're going to have 5, 0, 5. Okay? And then we're going to have a jump 0. The jump 0 basically attempts to check if the top of the stack is 0 and it pops that element out. Right now we have a 5, which means that we're not going to jump, but we're going to pop the 5 anyway. So after this instruction, we have 0, 5.
Five
Then
zero actually.
5, 0, sorry, 5, 0. No, it's not 5, 0, it's 0, 5. 0, 5. It is 0,
Oh,
5.
right. You're talking as the top of the stack is on the left. Okay.
Exactly, exactly. So 0, 5, then we do an over again, which means that you're going to have 5, 0, 5 again. Then we do a plus, which basically means that you're going to have 5, 5. And then we do a push R. The push R pops at the top of this data stack and puts that element on top of the return stack. So we are basically grabbing 1, 5 from the data stack and putting that in the return.
Yeah, we're
And
basically hiding it away. We will get back to it later, but for now,
yeah.
we're just setting it aside.
And then in the data stack, we put the number -1 on top of the data stack. Okay?
Yeah. And remember that the jump zero and the literal will skip over the triangle end and the -1, which means that the next word we execute is the one after that.
Wait. Can you repeat what you just said?
Yeah, the jump zero and the literal will skip, they advance the program counter, which means that right now the program counter is pointing to the word after the -1, which is the next word that we're going to execute.
Yes, which is this. No, but what about this? We didn't go through this.
We did. The jump zero tried
Oh yeah, the
to.
jump 0 attempted to jump to this. That's right. So we just ignore this.
Yeah, and
Yeah,
then the literal used the
we
-1
use the
after that.
-1, so we are at a plus. So after the plus, we have -1 and 5 on the data stack, so that means that you're gonna end up with -4 on the data stack.
Uh, just 4 actually.
Uh, so it's bottom minus top. Wait, I'm confused.
No, we pushed the -1 and we
Oh,
added it
it's a
to 5.
plus. Sorry, it's 5 and -1, so it's 4. Sorry, 4. Then we do a
Yeah,
pop R, which brings back the 5 that we just pushed into the return stack. So now we have 5, 4. And then we do an unconditional jump to triangle loop again. To triangle loop one again, right? So at this point, we should try to understand what this is doing, because right now we started with 0, 5, and now we are at the point we are doing another iteration saying 5, 4, right? 5, 4.
yeah.
And my understanding is that at some point this thing will be 0 again, and then this jump 0 will trigger, and we're gonna do some other things, and that's calculating something. For sure, that's calculating something.
It is. This example actually came from the paper because this architecture doesn't have a multiplication instruction. That means that the usual suspects that we use for like recursive function testing, which is factorial, is kind of inconvenient to express. So instead, we're computing the triangular numbers. The triangular numbers are computed by adding all the natural numbers from 0 up to whatever position you're in. Like, there's some wiggle room in the definition, but basically we're saying starting from 5, we're going to add 5 plus 4 plus 3 plus 2 plus 1, and that's the final result is the sum of all that.
So this is 15.
Yeah, that should be 15.
Okay, so at some point we're gonna reach the 0, and then we're gonna do other operations on top of the stack, and this return will return to here because this is the call.
Um,
As far as
yeah,
my understanding goes, of course.
it is. By the way, little fun fact, you can optimize this program slightly by taking advantage of the fact that we are being very literal about one line, as long as it's not empty, represents a memory address. We could glue together the beginning of the triangle loop with the actual triangle function and get rid of the jump up there.
Mm.
That's like that's like um, if you don't care, if you if you explicitly rely on the fact that, yeah, adjacent lines mean adjacent memory addresses, then we can do that. I wrote it like this because it's a bit higher level, basically.
And because I specifically ask you to try to utilize the most amount of instructions possible.
That too, yeah.
Yeah. So you may someone may say that this is over bloated, but that's the point. We want programs to utilize the entirety of the
Uh,
instruction set.
yeah,
Or
I
we can
mean,
do. I think we would need to do something like a with a vector, right? So we can cover all. I think
Which one vector?
like just use vectors like arrays.
the variable one does use an array of 4 items, basically. So there's
No, but
that. It
I don't
uses
think I understood what Mageta said. What do you mean by?
Just well, just to use references in a chain. Just that.
Oh.
yeah, the variable test actually does that.
Like allocate a position in memory that you store like three values. I don't know, something like this.
Ah, I see. Triangle numbers.
What?
Aha!
Opa.
plus
We have our first problem.
plus
That makes total
r
sense actually. That makes
jump.
total sense. This is a parser problem. So when I was doing the parser, none of the programs that I had in mind were considering just executing instructions randomly. Which is very, very not the case. So this else here, this else is basically saying, if you are not a number, a dereference, or a label, I don't care about you. So we're gonna have to do something
Right,
different here.
right,
We're gonna have to do
right.
something kind of different. And then this throw will be in the else of this if. Oops. There. Okay, so what is
Um,
the condition that you're gonna do there? I think I have an idea. I've
Actually, you could just put this if in front of the previous else, couldn't you? And then the indentation would be basically the same.
that works as well. Just because for me it's more, I don't know, maybe direct to just do it this way first, then I can refactor. And then you're suggesting to do oops, else there.
Yeah.
Okay, so I do have an idea on how to make that happen, which is to do something kind of like this. Something kind of like this. So we're gonna do something, just copy pasting for now. Later on we can refactor. I actually don't know what we're gonna copy precisely copy paste. mm,
Oh, I think I see what you're doing.
so
You
it
check,
should
you
be
were going
something like is valid instruction, and then we kind of pass the line ID, I believe. Something along those lines. Something along those lines. But it would be kind of nice. It would be very nice, actually, if this thing actually returns to me the instructions already packed, or it tells me that this isn't valid already. Because then I have to do two steps again, and I don't know if I want to do that. Do you understand what I'm saying? Like, you make something like ns array instructions. Oops. You do something like that, and then you say validate instructions, and then you pass the line. So in this case, plus pop r and jump will be on that line, and then this function will do all the processing, right? This function will do all the processing, like separating by spaces and so on. And then if the thing is actually invalid, we just do if null. Otherwise, oops. Otherwise, that means that we have something there, which is a validated set of instructions, and then we just bytecode appends to it.
Yeah, that works, I think.
So we're gonna do something like, um, ooh, okay, that's actually a little bit different than what I wanted. So okay, so this can't be an NS mute, it needs to be NS mutable. Yeah. And then you're gonna have to do some sort of concat, which I don't know the method to do it, but you're gonna have to do something like that. Yeah.
Um,
Why?
Probably on string. You gotta
Why
Why?
wait.
can't why can't the instructions just not be like what's the thing? I think it's an NSU integer, the name, right?
I have no idea what you're talking about, I think.
Like, why can't the validate instructions actually return the instructions already packed as in like already a
Oh,
number?
okay, we can actually do that as well. So uint, you're saying that to return already an uint 32.
Although that wouldn't quite work, would it? Because then we wouldn't be able to.
No, that would work. That would definitely work.
Okay, yeah, because then we don't have to worry about concatenating vectors. We're just pushing another value onto it. That's all it is.
Yeah. Okay, but in this particular scenario, we don't have an else if, we only have an else. And this exception here is actually gonna be down there, in here actually, there. So invalid instruction, blah blah blah. And then all these things that I copy pasted from before, I'm gonna remove it. I'm gonna simply remove it. And then this is this, I believe. Okay, so something got wrong with the ifs. Something got wrong. Let's try to identify which one.
I think you have an extra set of. Actually, you have an extra closing brace right before that last else.
No, but that is correct. This is the else that is closing that if there.
And then the next close brace is
Uh,
kind of spurious.
I think this
Yeah.
is wrong. What the? Emacs. There. And then this. Yeah. Okay. I think. Oh no, I think I understand what went wrong. This is the throw that I want to put in here. The other throw is the one that I copy pasted. Okay, I see. There and then there. Okay, now we're talking. Uh, okay, so after that, now we need to make this validate instructions function. So what this function should look like? Oops. It should be, I don't know, in the middle here. So it's gonna definitely return an uint32t pointer. Validate instructions.
Pointer.
Yeah, because we're gonna verify for null later. So what should we should give it a line. So ns string line. That should be kind of it. Then up here, I'm gonna make such function. So uint32t validate instructions ns string line, and what should be the this. So the first thing that I think we should do is to do something like this, right?
How
So
are you
these are
going to
basically
allocate?
tokens, and this is a line, and this is a line.
Are we calling
Then,
malloc
sorry,
for a uint 30? Are we calling malloc for a uint 32?
we are not calling any malloc. We're not calling any malloc.
But if we are returning a pointer,
And I just noticed this also needs to have the keywords.
What do you mean
Unfortunately.
by allocating?
like
Okay.
we're returning a pointer to an integer, right?
That's my idea.
But if we are returning a pointer to an integer, we can't just define the integer in the body of the function and try to return a pointer to it, because then we're returning a pointer to a memory region that's been deallocated after we
Mm,
return.
yeah, I see.
Actually, it doesn't really matter now that I think about it because the pack full word will tell you that you are wrong anyway. Like you, it doesn't. We shouldn't use null because the function that we are using, which is pack full
It,
word, will throw an exception if you try to use something outside of the keyword scope.
okay, that works. That actually works better then.
I think that should be it. I think that should be kind of it. What is wrong? I know what it
The
is.
place where it
Advanced
calls,
and map table keywords. Okay. So now we
and
can
then
go
the
to
place,
validate. Uh, Keywords. We do have access to
yeah,
keywords.
we are
This.
not returning a pointer. And then instead of checking if it's null, we have to catch the exception that's coming out of it.
Yes, we do have to do that, which I already forgot, so I'm gonna copy paste it. Try. I want a very, yeah, this one. There. So we're gonna do something like this. We're gonna grab that. Done, 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 done. And
You forgot on one line.
but what about this exception though?
Yeah, we're going to catch the exception. We're going to ignore it and then throw a different exception because ah,
I think this exception is better because it gives us location information. Something like this. And then we can just, oops, we also need to put this here. Yeah, so then we can just do that. And the value that we're gonna put is none of this.
instructions.
It should be instructions. And that should be it. That should be actual it. Yeah.
Fun times.
Okay, so what do you think about this, Marinho? Do you think this is enough?
Probably.
Probably. Okay, let's see the compilation errors. No compilation errors. Boom.
And it
uh,
loops forever.
yeah, definitely forever. We are just summing 1 to 5. That's definitely forever. Ooh, that's a fun one. So, how do we start debugging this one? Okay, I have a proposal. So let's go to the VM. Let's go to the VM and let's go to execute and let's comment this
I
line.
was thinking debugging this would be hard
It
if we
will
ever
be,
find something.
it will be, but we're
So
gonna.
we should not write bugs, right? That's what we should do. I literally been told that. "Oh, but what if you do that and that's a bug? Well, you should not write bugs. Wow,
Genius,
that
man.
solves all my problems.
Genius.
Thank you.
Genius. Okay, so boom. Okay, okay, now it's the fun time to see if it's the logic or if it is uh, the actual the actual parsing. That's very very important. Control this. Um, Triangle there. Okay, this is enough. And here we go. So
Literal call.
the
Yeah, I
the
remember
call
call
is
is
4.
4.
The halt is definitely 6 as well. Then we have a literal tree is 20 again. Jump In conditional, it's
which is
1.
1.
Then we have over, which should be 11. Then we have a jump 0, which should be true, yes. Then we have an over again, 11. Then we have a plus, which is 25, yes. Then we have push R, which is 9, yes.
Which is
Literal
9.
20. Uh, then a plus, which is 25, yes. Then a pop R, which is 10.
10.
Then we have a jump again, which is 1. Then a push R, which is
Wait,
9. What?
why do we have another jump? Oh, right, because it's looping. Right,
Yes,
right.
yes,
That's
yes,
correct.
yes. Then we have the push R, which is 9. Yes. Then we have a drop, which is 13. Then we have a pop R, which is 10 again. And then we have return, which is 5.
Which is 5. Yeah.
I think that means that my parser is awesome. That's what it
Your
means.
parser is awesome. Um,
Okay, so that means that the execution is wrong. That means that the execution is wrong.
1 second. We jump 0. Man, this would be so easy. The triangle end would be way easier to read if we had swap. But okay.
Okay. Okay, so now let's go through the options, right? So I think that for sure it's something in regards to the jumpings. Like it needs to be one of them that must be wrong, in my opinion. That would be the first one that I would check. So I'm gonna
Right.
uncomment this
So,
line and remove this one. So now we have back the infinite loop. So let's go to jumping.
um,
Jump. Okay.
can we do a thing? Like, I know that for halt, we are printing the top of the data stack, right?
Yeah.
Um, since this is a loop over 2 variables, essentially, can we do can we print the top 2 values whenever we jump? That would be very convenient.
Of the data stack?
Of the data stack, yeah.
Sure. Sure. So whenever we jump, so it's actually here that you want that. Let me actually go to the how we do that in the VM. Yeah, here. Thank you very much. So you want to see. Ooh, you want to see the first two of the two data stacks actually, right?
Yeah, the top 2 values of the data stack.
Oh, the top two values of the data stack. How are we gonna do that easily though, without messing around with the program? Uh,
Uh,
like you can drop and then push it again, pop and then push it
yeah,
again.
yeah, that's probably the easiest way to do this.
Okay. So I'm gonna steal this code and I'm gonna say data stack 1. I'm gonna pop this, then I'm gonna peek again, saying that this is data stack 2, and then I need to push. Push. Yeah, something like that. ns log. And then I'm just gonna put the popped value back. Sounds good?
Sounds good. Let's try it out.
The problem is breaking this shit. So let me remove from the parser. No, not this.
Hmm.
Uh, yes. Okay, so let's try to build. There are wrong things happening. Use of undeclared identifier data stack. What do you mean? Oh, it's not this, it's self. Oops.
Self dot data stack. Yeah.
Yeah, there. Go. Okay. Then we run, and I need to be very fast.
Very fast and wrong, like it usually goes.
What happened? That's supposed to be. Huh.
Okay, so whatever is wrong is very, very wrong. Oh fuck, I was not fast enough, man. Okay. Was this faster? No, by any means.
Oh, wait. I think I know the
Oh
problem.
no, I was fast
Maybe.
enough. Okay. Wait, wait, wait.
I
05? 05? Okay. This is the
I
this is
think
the
I know. I think I know the problem. You are assuming that the integer that we parse will be a 32-bit integer, despite the fact that you are running on a 64-bit machine,
sure.
which means that actually there's a bunch of zeros in the place where there should be a bunch of ones, which is not what we want.
What? I have no idea what you're talking.
I'm talking about the sign bit. The sign bit means, like, since this is -1, the bit pattern should be all ones, like all the way from right to left, right? Right being the
Sure.
least significant bit. The problem is that since you are parsing this as if it was a 32-bit integer and chopping only those 32 bits, this means that the bottom half of the number is all ones and the top half is all zeros, which is not actually a negative number.
I don't know if I buy that argument. Let me check a thing. Uh, yeah, okay, so this is correct. You think it's because of the bit representation? That's crazy. That's really, really crazy. Don't you? Let's read this first though, before going through that route, okay? Because apparently this was fast enough. So the data stack, when we do the first jump, which is this one, it's 05, which is correct. You agree with that?
It is correct.
Then we do a PC fetch because we always do that. Then we do an over, jump 0, over, plus, pushing to R, fetching literal, PC fetch. 1, 2, 3, 4, 5, 6. So we actually need to do a PC fetch. And then we have a plus pop R jumping. And then we do the other jump. We have the 5 actually went correct. Because at this point, I think we should have like 5-0 or something.
Yeah, it should be.
Oh no, it should be
Is there?
5-4.
It should be 5-4. Yeah.
It should be 5-4. And we have a lot of garbage here. So which instructions here could be the wrong ones, considering that?
Let me do this real quick. So, like, look, I have a Rackets repo open here because I just happen to have one. So -1, and then I'm going to bitwise end with the binary value. Uh,
No, you're testing the bits hypothesis.
see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I'm just writing out the bits by hand. 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, and 1,
Definition
2,
of
3,
insanity.
4, 5, 6, 7,
What do you say,
8.
Magenta?
Definition of insanity.
But we're messing with the VM. We need to do the bits thing. Imagine if the number 4 in the 32 versus 64 thing is this number there. I'm gonna be really impressed by that.
The one Right. So if I bitwise and -1 with a mask of all ones, 32 bit wide, I get the number 4294. That long number over there, except it ends with 95 instead of. It ends with 295 instead of 300, right? So we literally just added 5 to the highest possible unsigned 32-bit integer.
So it is what you said.
It is what I said.
Wow, I'm impressed.
Yeah,
Okay,
because if since we are in a 64-bit machine doing 64-bit arithmetic, actually -1 should be a much higher number than that when printed out as an unsigned number. It should be, in fact, this number, this very big number that I'm going to post in the
no, but that's
chat.
not. But that's not what we got when we did the -1 before. I think we are
It
handling
isn't.
32-bit things, man.
But that's the thing. The machine you're running in is a 64-bit machine, right?
Yeah, but the representations in the code is 32, as far as I'm aware.
No, 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 no. Go to the plus instruction. Go to the plus instruction real quick.
Plus here.
Yeah, so see, we're taking NSC integer value 1, NSC integer value 2, we're adding them together, but NSC integer is a machine width integer, which is 64 bits in your machine.
Oh, you think it's because of the representations of these things.
And the parser, what
No, the
does the
parser is
parser
doing
return?
32. The parser is definitely doing 32.
Yeah, that's the problem. The parser needs to agree with the actual implementation. It has to return an NS integer.
Yeah, but then we are fucked, right? Then we
Why?
lose the Mac cube, whatever generation.
We No, we don't. We'll just have different behavior if the machine is 32 or
Yeah,
64
we can
bits.
do a compiler flag or something.
No, no,
Yeah.
no. Marinho is going further, Mageta. Marinho is saying that we just depend on the architecture.
Just a sec.
Uh,
Uh,
I don't know about that, man. I really don't know about that. Let's try that.
well, the other alternative is to replace all the machine with
Yes.
arithmetic in the VM with 32-bit arithmetic explicitly.
Yeah, yeah, yeah. But that would be very inconvenient. Very, very inconvenient. I wonder if there is the flag that Mageta proposed. That would be so helpful.
Yeah,
So
there
if
is it's a compiler directive, right?
Yeah, actually,
Well,
it
what
wouldn't
is
even be a. It
well, if
wouldn't
we can
even
find
be
a
a.
generic solution that we don't need to rely on the flag, that works.
no, but
Like
this is a
what's the
generic. What Marinho suggested, Mageta, is a generic solution. Look, when building 32-bit
yeah, I get it,
applications,
but what's the problem? Why didn't you want to rely on that?
I don't want. It's not that I don't want to rely on. It's just because this is the type of stuff that I would like to be 100% sure that I'm handling 32 bits. And if I do NS integer here, for instance, now I have to remember that this is architecture dependent. It's not readable, 32. Which in this particular instance that we want to maintain backwards compatibility, it's something that I really would cheer for. But I think it's fine. I think it's fine.
Let me give you a data point here. Racket and chess scheme underneath it, they do in fact have different with fixed nums, which is how they call. They are not quite machine width because you have to lose a bit to tag if that it's not actually a pointer but an integer. But that's how they call their machine width integers, and that actually has a different size depending on their architecture. Of course, since it's a Lisp, you don't usually care because if the number were to overflow, it just promotes to a big num, so you still have correct arithmetic either way.
Hmm.
But that's something to keep in mind. Some languages runtime do that stuff all the time because you may want to run in a Mac Cube, for instance.
which is not an unreasonable request, by the way.
No, I never said it's unreasonable. Anyway, do you think? Do you need to cast this thing here? Do you guys think
You need
so?
to cast like the pack forward is fine because we're deliberately saying a word as far as machine code execution goes is uh, well, but that would create a discrepancy, wouldn't it, between yeah, that's not very nice.
No, what discrepancy are you talking about?
Like if we say that we explicitly handle the problem is if we handle NS our assembly language is going to be architecture dependent then, which I mean it's an assembly language that's kind of reasonable, but what I'm getting at is if we go for like proper 64-bit words or 64-bit machines, we actually double the number of instruction slots in a word, which changes how we parse lines, and it's probably better actually to change the arithmetic to be proper 32-bit arithmetic instead.
No, but my understanding is that if we are at a 64-bit machine, because the rest of the code is implicitly assuming 32 anyway, it doesn't really matter. That's my understanding.
Uh,
Although I
I
agree that
guess that works. Like for packing words, it doesn't actually matter too much because it's just code. What function are you using to actually parse integers, though?
I'm using the Objective-C transformation ones. Oh man, for some random reason my Objective-C mode doesn't have the shortcuts that I want. And that, I hate that. I
You
totally hate that.
mean
What is happening with this
you?
function? It doesn't have a name.
No, it does. It's from 64 to 32.
Yeah, but the parameter doesn't have a name. How does that work?
Oh, I see. I see. Yeah,
Okay,
that's
so I have
weird.
no idea how that works. Anyway, so I'm gonna just do ns integer here. And again, if we change our minds in the middle of the way, this is easy to fix. It's just renaming and like we can just query replace everything here to be uint32 or whatever. Actually, so now that we are changing that, we need to go back to the VM because now the VM is wrong. Um,
Is it though?
I believe so, yes. Is the VM wrong? Oh no, we are just using ID. Okay, so I think it's fine. I do think it's fine. So is this enough? Is this enough? What I just changed here to be NS
Um,
integers? We need to discover how to cast this shit, but aside from that,
Look at how you talk about your code, man.
no, actually, that's not really the problem. The problem is not there. The problem is that -1 is parsing as a number that's not actually -1. Like the packing words and all that stuff, that's fine. The problem is parsing integers.
but how are we gonna fix that? Because the is number. I'm using this.
Yeah, and it returns number integer value. That should be an NS integer. You just have to get rid of the cast then, don't you?
Like that.
Yeah,
Okay, so do you think everything else is gonna work?
I mean it
Did I
should, I
save
think.
everything? Save projectile. Yes, I did. There. Okay. Boom. 15!
And there we go.
Again, Marinho was right. So it was a incompatibility between what the VM was expecting and the architecture that I'm running the thing. So now we need to make a decision. Are we gonna make the VM architecture dependent, depending on if it's 6432, or are we gonna pinpoint like
I mean, technically, the only difference between only behavior difference between 32 and 64 bits right now is that the range of integers we can represent in a 64-bit machine is higher.
No, but we
That's
don't care
the
about
only
that.
difference. That's the only difference. And if we don't care about that, then that's just the way it is, I guess.
Okay, so we are fine with making it. I don't think I got what your point. You're saying that the best way is.
We can just keep it the way it is. We just have to keep in mind when we are doing 64-bit stuff that right now we only consider the bottom 32 bits for the actual code, like in case of for the purposes of executing code, like we ignore the top 32 bits because that doesn't exist in all platforms.
Mhm,
Which
mhm.
means that actually, when we write a number to memory, the value can be much higher than what we can pack in an instruction.
Yes.
I don't know how I feel about that, but I guess we can just live with this. It's it's just a quirk in the
You're
implementation.
basically saying. I think you're basically saying that if you go in your program and you do something like this, it will allow you to do it like that. It will allow you to do it, but it's not gonna behave as you might expect.
Yeah, if you just write a zero um, at the highest place in a 64-bit number, and you expect when you interpret that number as a word that it will fetch the next word because the top value is a zero after all. That's actually not gonna work. It cares about the top value in the bottom half only,
Yeah. Yeah,
but
but I
only
think
on
that those are minor
64-bit machines.
details.
But only on 64-bit machines. On 32-bit, we're fine.
Yeah, but nobody aside from Baguetta has one of those.
Oh man, you're underestimating the ability of the community of old computers. You really are. These people
Yeah,
are
man.
craving for
Actually,
old software, man.
yeah, that's actually a thing.
No, I believe him.
Um,
I'm not saying that he's lying or anything. I'm just saying that if you compare the markets, I have a very strong feeling that the 64-bit machines are more common.
To be honest, I think since it's a hobby project, I think the engagement might be even better in 32-bit than 64.
yeah,
Okay,
because
let's put that to the test.
what I was actually gonna say is for Salem, because Salem is also, it's a language runtime, so it has to care about this stuff as well. Um, I deliberately I deliberately restricted myself in the design of how I'm going to represent data in such a way that it's compatible with a 32-bit machine, even though that means I can't use the full potential of a 64-bit word.
Yeah, no, I
You see?
understand. I understand, but well, anyway. Uh, I
You
think the
heard
only thing
words
that we
from a
need to do
wise
now,
man.
now that we have 20 minutes left, I think the only thing that we have left to do is to do the change that Marinho suggested about changing the syntax of variables to use another symbol. I think that's very reasonable. So that's very easy. So it's just going to the is variable line, right? Is variable line, and actually this is still true. This is variable. What we need to do is actually change the other condition. Because something that I didn't tell you guys, I am exploiting the fact that this if was done already.
Yeah.
So I'm asking if this is a label line, and if it is, yeah, yeah. So when I am in here, I already know it is, right? I already know it is, which means that I can just ask if it's a variable line, right? But now that's not going to be true anymore. That's not going to be true because we're going to have to do an else if asking is variable line is variable line. So I'm actually gonna have to change that function, yes. So is variable line, yes. So this is gonna be a condition of two things. a condition of two things. It's going to be this and is the string starting with tab. Tab doesn't work. I don't think that it is tab, Mageta.
Oh no,
Line.
you need to activate YAS mode. Do it
Uh,
again. Meta X.
I'm gonna do it shortly. 1 second. And we want to use this symbol right now for the thing. Okay,
You need to enable the YAS snippets mode
I
for
see.
that to work.
And then else, and then that. Yes. So if it is a variable line, this code gets it's not gonna live here anymore. So let's grab that and let's put it here. There. So if you are not, wait a second. I think I did in the wrong if. Yeah, I did in the wrong if because I am stupid. Okay, cool. That's not the if that I wanted. That's not the if that I wanted. Emacs. Okay. Else if this is what I wanted. Oops. There. There. So actually this can be this. Okay, so now it's impossible for a line that is potentially a label to be a variable line as well. It is impossible, which means that this if doesn't make sense anymore, which means that I can just do this, and I can just remove this in its entirety. Next, uh, next. So if is this a variable line? If it is, I'm gonna grab it, and what's gonna be this thing? Oh, I need the first one. Yeah, I need the first one. Sure. So we're gonna do um, variable
Name, I guess.
label, variable label. Uh,
Hey,
Oh, hello, Sophia.
Hello.
yeah, but I need to pop stuff. We need to definitely pop. So first char get out of here. What do you think about this, money? So we are grabbing the line, which we know it's we already know because of this. We already know it is a compile time variable. We know that. Then we grab it, pop the first char, which means that we are removing this special character. Then we grab the token, grab the number because we need to remove the hashtag, and then we're gonna put in the variables map that number using the variable label. Does that sound
Uh,
reasonable? And hello, Sophia.
hello.
that sounds reasonable. One thing, we have to change the definition of an empty line to also include what do you say? Uh, variables, right? Because
But only in the second pass, right?
no, in the
Might be
first pass
fairly
as
easy.
well. The first pass as well, because the first pass is where we collect the memory addresses for the labels, right? But variables are not going
Mm.
to end up in the binary image at the end.
Oh, that's right. That's right. We need to jump them. We
So we
kind of need
just
to
have
jump
to,
them.
yeah, we have to change the definition of whether a line is empty to check also if it's empty or if it is a variable. If it's a variable, we treat it as if it were empty.
No, but I'm confused. In the pass one of the program, we cannot jump the compile time variables, right? We cannot just do that because then we're gonna lose their definitions, right?
Right.
I
But we
think
have to like if is line empty, da, 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 da,
I think what you're
else if
talking
is
about is actually to add a non-empty lines counter to this block as well. Like, do you see
uh
the problem? Like,
no,
what you're saying
no,
is
actually
go.
Actually, we have to decrease the non-empty lines counter from there, I think.
Decreased it. That's interesting.
Yeah,
Decrease it.
because you see, we know that the line is non-empty because it's a variable, right?
Yeah.
But actually, we have to treat it as if it was empty for the purposes of counting the memory addresses. So we have to decrease it to counteract the fact that we're going to increase it anyways.
Oh. Okay, I think I see. I think I see the math. Okay. Okay. So this is pass one. So now we are basically grabbing the variable with a different character now. We're not going to use the same character as before. Cool. Pass two. That's when we... Do we care about the pass two actually? Do we need to change anything?
Do we need to change anything?
I don't think
Huh?
so. We never cared about the variable labels in this pass. We only cares about numbers, addresses, the the referencing, and if you have random instructions spread
Oh,
out.
right. In this pass, we have to check. Right now, we are checking if the line is empty to decide if we're
Yes,
going to
yes,
do
yes,
stuff.
yes. Or is variable line, right?
Is variable line
Actually,
indeed.
and here in this particular case because it's negative there. The Morgan law. Uh, and it's not is variable line line ID. Is that what you're talking about?
Yes, that's what I'm talking about.
Cool. Okay, so now we should be able to run this program, right?
I think so. I don't recall off the top of my head what I was thinking when I wrote it, but I guess we can try it out.
We don't know what the program is supposed to do.
Let's see.
Yeah, let's fix the sum
We
first though, because the sum is now wrong.
right.
Okay, let's see if the everything goes alright. So just build. Okay, nothing too crazy. Chime samples sum GHF and keywords this. And something is wrong. Could not find token at position 1 in line first number. First number. So I think
Asterisk.
something didn't work. There's a very cool way to check if this worked. So we just go to the print in here and we're gonna check what the pass one did. Uh,
The best one is the one that's
no,
throwing
the
the
pass one is
exception.
breaking actually. It is the
Yeah.
pass one that is doing wrong. Okay, so definitely not cool. Definitely not
Oh, I
cool.
think I see the problem. How
Oh,
are you deciding which character represents a variable definition?
uh, I am checking by doing this. So it's this character.
Yeah, your condition is backwards.
What do you mean? I have no idea what you mean.
You're checking the second value, the second token in the line before checking the first character of the line.
What's the difference?
Short circuiting.
Oh, okay, so this is this is C, although it has those sort of tricks. I forgot about that. I actually don't know if this should make any difference, but let's see. Oh yeah, the instruction plus is invalid in Chime. The instruction plus. Yeah, that makes sense because now we are using this plus. 69. 69. Okay. Okay, so now you gotta do me a favor, Marin. Please remember what this does.
Right, so we grab the address of the thing, which is a memory location that initially contains 1. Then we do a push A, which means we put the address that we just read the data stack into the A register, where we're going to do some operations on it. Then we do load A, which dereferences the address in the A register, which we just set to be the address of the thing. So at this point, we should push a 1 to the data stack.
Wait. I think I already see the reason this is not gonna work.
Why?
Because when doing the second pass, it's gonna identify this as a label, and then it's
Yeah.
gonna try to push whatever it remains as instructions.
Oh, right. Then it has to check if the first token after the label is an integer, and if it is, we push an integer instead.
So is that a corner case? Is that only when you have only numbers with the label? Um,
Um,
that's not what I want.
hmm, only numbers. Let's see.
Yeah.
I mean, technically, if we want to be cheeky, we could say, okay, this is a variable, but instead of having a number, it contains a function pointer or another pointer to an array or whatever. And then, yeah, it doesn't have to be a number. It can be a number or a variable, like a compile time variable that we're dereferencing, or it could be actual code as it currently is assumed to be,
Oh, that's
or
very
it could be a
interesting.
memory address. Yeah, it could be anything really.
Okay, so what you're saying me is the following. Pop. Okay, so what you're actually saying, which is that's important. Token at expects a string. Okay, expects a string. Is this already separated by spaces? Yes. Thank you very much, Pest Lemos. Pack this. So what you're saying is the following. So we're gonna grab the second. So we're gonna do something along these lines here. So second token, and we're gonna ask token at line at position 1, right? We're gonna try to do that. I'm very confused. What are you? Oh, it's line ID. It's line ID. Let's comment this for now. There are three possible cases there. Or it is a number. Oh, I don't have the thing.
Yeah, it
Uh,
can be a Actually, there are four cases. It can be a number,
it can
it
be
can be
second
a
token
mem,
number, or it can be a dereference, right? It can be dereference.
or it can also be a memory address. And then
So
the fourth
second
case,
token, memory address, so it is basically address line. Second token, and
the fourth case will be in the else, not in there, I think, which is in the case where it's actual code, and then we pack the instructions as usual.
okay, so else. Um, okay, so that means that we're gonna grab this code, do this, grab this line, do this, that, kind of like that. What is wrong with my? Oh, there I'm missing a D probably, right? Yeah.
Yes.
So what do we do when we have any of those?
We parse the second token, and that's the value we put in the memory, basically.
Okay, so you're basically telling me that we have like an NS string value that we're gonna pop the first char out of the second token. So we remove the special
Yeah.
characters such as star, column, no, star, ampersand, and um,
Hash.
hashtag. Yeah.
Yeah.
And then we're gonna put that straight up to the bytecode.
Yeah, we parse it and then we do whatever is expected. So if the first char is a wait, pop first char already does that, doesn't it?
Does what?
Like we have to actually do whatever is expected. So like if the first char is a hash, we just parse a number and that's the value at the memory address. If it's an ampersand, that's a memory address, so we have to do a lookup
That's
in the
terrible. Okay, so we're gonna do the other style. So we're gonna do separately these things. At least for now. Maybe I'm gonna refactor this later. But for now, it's gonna be something like this. So maybe it's gonna be dref. Uh, there. And there's another one missing, right? So else if there, there, there.
Is variable whatever.
It's is address
Is
line.
address line. Yeah, is address line.
Okay, so in the particular case, we're gonna do this basically, potentially something similar to this all the time. So what do we do when we have a number? We just straight up put into it, right? Straight up.
We just straight up push the number. That's it.
Yeah, so my understanding is that I'm gonna
And
grab
get
this line and I'm gonna change the name of this. So this is a number for sure. And then we do that. Second one is a dereference. So we need to do a lookup, right?
pop first char, second token.
So this is like a label. Yeah, a variable label actually. A variable label. So I need to do a
Yeah,
lookup on that.
then we have to do a lookup on that. And whatever value we look up,
Oh, the copy pasting, man. We should make functions, man. We should. We should make functions. Uh, so in the case of a dref line, that's what we want. So we're just gonna do a lookup, and if it is there, that's not the case. So this is second token. Wait, is this second token? Actually, no, this is not second token. This is label in here. Label. We need to pop the first char there. That's cool and all, and then we do kind of like that, and everything else goes accordingly. Everything else goes accordingly. There. Okay, next case is when you have an address line, and again copy pasting for the win. So this.
yeah, I think if you're going to refactor this later,
These should all of
one
these should be
suggest
functions, man.
Spoiler, we probably will not.
I will refactor this for sure.
one suggestion is check if the first thing check if the very first thing is an address. Oh, actually, let me put it this way. First, you split the line by white space, right? And if the first thing is a label, you just get rid of it and parse the rest of the line.
Yeah, that's what I do. This is already happening here. I think I have to double check because now this thing is there's so much more code, man. Okay. Cool. So and the else case is basically the previous normal case.
Yeah.
So if you have a number line, number, yes. If you have a number line, this is correct. This should be second token, yes. And the second token here. Yep. Does it work though? I have no idea. It compiles. It compiles. We have 69. Do have 69. Let's go back to equality for a moment. Equality. Wait!
No, that's -1 64-bit version. It's correct.
Okay. What other thing? Triangle numbers. So
Triangle numbers.
numbers. 15.
15 still works.
It still works. Instruction coverage is not a program. We can't run
It's not.
print because we don't have syscalls. So the only remaining program
It's variable.
is the variable one.
So yeah, we grab the address of the thing, And initially we expect the thing to be 1, the value of the thing to be 1, and there's 3 zeros very deliberately after it. Then we push the address of the thing to the A register. We load the value from the A register, which will do a dereference. So we now have a 1 on the top of the data stack.
Yeah.
Then we double it, which just does a shift left. So now we have a 2. Then we copy the 2 and we store a plus, which will put the 2 at the address that's in the A register. So um, the value of thing was 1, now it's going to be 2 in the
Yes.
actual memory. And because it's a star A plus, it will also increment the address in the A register. So now we're pointing at the 0
The
right
first
after the
0, right?
label. The first 0, yeah.
Yeah.
So we basically do that a few times and then uh, doubling the value each time from the top of the data stack. So like,
So then the final
uh,
number is 8 or something like that.
let's see, dupe double. So we
Oh no,
store
but
a,
the other rounds we are doing load A plus, which is different than load A.
yeah. So we store a 4 and then we store an 8 on the next address. So the thing will be 2, then the first 0 will be 4, the second 0 will be 8, and then the final 0 will be 16. Then we grab the address of the thing again. We push it away to reset the address, right? Because we did a bunch of increments in there. And then we load 2, 4, 8, 16, and we add them all together. And the end result should be
28.
28.
Yeah, you said 2. You said 2, 4, 8, and 16. No, this is 30, actually. Am I
It
right?
is. It should be 30, I think. Yeah, you're probably right.
Uh, I have very strong feeling that's not what we're gonna see. But at least we are gonna be testing exhaustively our store and loads, which is important. Which is very, very
Uh,
important. So variable. Of course, double is not in my keyword set.
just rename double to yeah. You
It's
have
easier
to
to just
rename
do
it
it here.
to
Store A plus. I'm gonna already change this as well. Load R
plus
plus.
plus, not plus. We're not dealing with an infected wound here.
Go. Stack underflow. Attempting to push value to undefined A register. We are lacking hardware, my friends.
we never initialized the A register. That's kind of sad.
um,
Just
okay,
set it to 0, man.
okay, so basically execute. Uh, let's add hardware to our computer. There.
There.
Okay. This case I do need to do it like this. I have a feeling that's wrong. I do have a feeling that's wrong.
Fetch literal, push to A, load A double, dupe, load A plus. See fetch dupe, double, store A plus. Yeah, we store 2, and then we store.
Push
How did
A,
you get
load
that?
A, double, dupe, store. Oh, that's wrong. Yeah, that's wrong.
What?
This is
What is
this is
wrong?
a this is a store A plus and this is a load.
Yeah, that is wrong, actually.
Okay, now it comes the problem. This smells like a parsing issue for the first time. how do we know that? Okay, so let's go to utilities and let's uncomment this line in particular. Let's go to the code. Let's ask to print it. And let's go through those numbers there. So control opcodes there. And I'm gonna go to our variable. Yes. Okay, so the first thing is a literal is 20. I already remember that. Push R, push A, sorry, push A should be 7, yes. Load A should be 14. Double should be 26, yes. Dupe should be 12,
It
yes.
is 12.
Store A plus should be 17, and it is. Which means that the problem is probably on vm.m when we are doing op load a. Actually, we want to do store A, right? Store A plus.
Or A plus, yeah.
Store A plus. And no, we are not calling the load by accident, as I was thinking. Which is sus, which is rather sus. Let's go to the code. Oops. So VM plus, yes. So let's go to store A plus. Yeah, the codes are different. Definitely codes are different. So how the heck are we printing load A?
Oh,
How
I
are
don't
we
know.
printing load A? That doesn't make
I mean,
sense.
we do have a load A, but it's not a load A. Yeah, we load A first and then we store A plus.
No, yeah, but do you look at the prints here? So after the dupe should be store A plus, right?
Yeah, it should be.
It should be store A plus, but it isn't. But in the code, it's saying 17, which doesn't make sense. Doesn't make sense. So 27, 14 is the load, the double is the 26, the dupe is 12, and the load A it shouldn't be load A. That's the problem. And it's a load A plus, which is rather even weirder. Load A plus. What's your code, my friend? Opcodes. Load A plus. It's
It's 16.
16 instead of 17, even though it's saying 17 here.
Maybe the dialect has been flipped for some reason.
It is a possibility for sure. Let's go there. So let's go to the keywords. So store A is 15. Uh, store A. Wait, there's something wrong in here because the store A is line 16. You see here on the bottom here.
But line counts are one based, right?
Oh yeah, this is Emacs. I forgot. Okay, so it is correct. But so I didn't swap them. Look, the load is coming before the store. I
Okay,
didn't
so
swap them.
how the heck are we doing
A
what
load instead
happened?
of a. I have no idea. How are we doing a load instead of a store? How
That
are we
sounds
doing?
bad. It's bad, right?
No, it sounds it sounds bad. Of course, the parser says star A plus, and the executor, the evaluator is saying load A plus.
What the
Yeah, it
heck?
sounds bad. Yes, it sounds bad. Variable. Yeah. So I think we're gonna have to call. I'm gonna have to call it for the day. We already are in for 2 hours. I think we did a lot of progress. We expanded the parser. We checked not almost all the programs that we had available to test to see if our implementation is correct.
Yeah,
Uh,
this is actually the last one that doesn't require syscalls. The other one, it needs to be translated to the new syntax, and we need syscalls to actually print stuff.
and we have to decide which design we're gonna do, because I think you mentioned two paths to implementing the syscalls. One of
Yeah, we
them
can
is
implement. Yeah,
removing
we can.
go.
Yeah, we can implement a syscall opcode and then do stuff with that. Like we push the syscall number,
Hmm.
executes the syscall instruction, and then whatever that's meant to
It's
do, we do
like
it.
a normal assembly, right?
Yeah,
Normalism.
yeah, pretty much.
Um, the other option, the one that doesn't actually require to implement opcodes, is okay. So we have signed numbers. We can just say if we try to read or write from a negative address, that actually corresponds to a memory mapped device, and then we can do I/O that way. That's the other alternative.
Yeah, that's the other alternative. And you also need to fix the what the heck is going wrong with this program here. We also need to fix
Yeah.
that for sure. And the weird thing is that Story Plus is appearing after. Right. Story Plus is appearing after. Which is,
Let's
again,
see.
really so weird.
You see fetch, fetch literal, double, then we duplicate, then we do a load a plus, which is wrong. It should be a store. Then we
Yeah.
do a fetch, that's correct. Then we do dup double and store a plus.
Which is correct. Then a dupe, then a double again, then a load
Oh.
A plus. The second stores, like the ones at the last position, they are becoming loads. Do you got that? Like this load here should be a store. This load here should be a store, and they are always the last one, the last instruction.
Hmm.
Maybe
Maybe
that's
there's a
something.
corner. Maybe that's a corner case related to the fact that it's the final instruction slot. Maybe I don't know. We'd have to
If
look at
we are
that.
jumping one bit over, the 17 will become 16. Because 17 is basically having like 16 and 1 at the end there, right? If
It
we
is.
are ignoring the least significant bit, that becomes 16, which becomes a load.
That is correct. That is actually correct. Okay, that's a problem. That's a big problem.
But then, how does this program doesn't work and all the other ones worked? That then we have a bigger problem. If what I said
Go
is
back up.
correct.
Go back up to the logs. I want to check something real quick. Or better yet, try to run the other programs, like just one by one. We look at the instructions that we're printing, and I want to check one specific thing.
There.
20, 20, 25. Um,
I think
that's not the
I know
last
what you want to
instruction.
check.
Yeah, is there any other case where the final instruction slot is an odd number?
No, that and I was not guessing that. I was guessing that you wanted to know if before doing a call or a jump, we fulfilled all the six slots. Because maybe that's never happened ever. Like this program also know the last one is the triangle numbers. Jumping, jumping. Yeah, maybe we never did that.
Like, is there a case where there's a PC fetch and the previous instruction is not a jump, is not a call, but is an instruction that has an odd opcode, an odd number opcode?
Before that, let's just go to utilities and see if we identify something fundamentally wrong. So I create six slots, initialize them with 0. I go from 0 to the amount of instructions that I have. I check if the keyword that we are getting exists in our keywords map. If it does, I basically grab that opcode and put into that position, and then I call pack word, right? Then I call pack word. Something that is bothering me is that this is an uint32, but we are returning NS integer.
Real quick, go to the part of the evaluator that decodes the opcodes. Uh, Real quick.
VM. Collect.
I think NS integers are already 32.
It is architecture
Yeah,
dependent. NS integers.
No, NS integer or NSU integer?
Both are
they
Both.
both
architecture
are.
dependent. Here, this is the NS integer, and look.
Either way, I don't think that would be a problem. We'll just stretch the bytes.
That's true. Here's the function that you are interested in, Marin.
Yeah, line 61. That's actually a bug that I fixed, and apparently there was a regression.
Did we merge that?
We did. We
Okay,
totally
so
did.
definitely this is a regression. So what should be in here?
It should be instead of the number 8, it should be open paren, and then you're going to write a 1, and then you're going to shift the 1 to the left by 2. So, yes, with spaces in between because that's how I
Oh, I
wrote in
remember
the
this.
PR, but
Yes.
Okay, so is there any chance this is the solution to our problems?
it is actually because the bug I caught is that we were masking off one extra bit that we shouldn't be.
Um, it fixed the problem. It is still wrong though. So that's progress anyway. That's progress anyway. So now we can at least go through the instructions and see if they are being correctly mapped. So after the dup, now we do have a store a plus, which is correct. Then a PC fetch, which is correct. Dup double story plus, dup double story plus, fetch again, double story plus, fetch literal, push to a, load a plus, fetch again, um, plus, load a plus, plus, load a plus, plus halting.
Okay,
So
the instructions are correct. Um, I forgot to write down what the final result was supposed to be, but
we
I
are
don't think
not
it was
out of
supposed.
the way yet. There are two things that can be wrong that are not being printed. First is if the decoding of the parser with the things that we just added, if that's being done correctly. We don't have the
Yeah.
memory here to see. And the second thing is the implementation of any of those
Right.
can be wrong.
Yeah. Right. It would be very nice if we could do a memory dump at the end as well.
That's the thing. I don't think I have that. Wait, you say memory dump? You're basically asking me to give you the byte to print the byte code. I can do that for you.
Yeah, just print out the memory. Like, it's going to be an array of integers, just print the array of
It's gonna
integers.
be
That's
unreadable,
literally.
but we're gonna try.
But for this particular example, we only actually care about the far less numbers.
Um, oops. So how the heck do
That
we
should be.
print a mutable array? We have this in the VM. Oops. VM.m. So there is something like a print state. Yes, I remember that.
That's a
Uh,
that's a print stack though.
there.
Oh, but the stack has a mutable array inside of it, so that should be fine.
So um, byte codes, and then instead of RAM, well,
Uh,
actually, I'm gonna maintain it as RAM.
no, I actually meant not print out the parsing
Here,
output. I meant
actually. So we're gonna
okay.
ignore the big numbers because they are basically the packed instructions. Variable. So
Yeah,
we
the
only
number
care
six
about
is
this and these.
yeah, the number six is correct because if you count out six, index six is the number one. So 0, 1, 2, 3, 4, 5, 6, 1.
So 6 is
And
here,
then the
right?
last, yeah, six is there, so that's correct. And then 1, 0, 0, 0 is also correct. And then um, we can just do the same thing, except we can print out the RAM after we execute the codes, and that should tell us if we did the stars correctly.
Oh, okay, that makes sense. Okay, so you want to go to vm.m halt, and instead of just doing kind of this, we want,
We do that too, but we also print the RAM, yeah.
yeah, so ram halt there. Okay, boom. I have no idea at all if things are correct. No idea
They
whatsoever.
don't look correct, actually.
How do we manage to change the places where we had instructions? Like this should never change, right?
Unless we do a star to zero to address zero, which I don't think we're doing, it shouldn't change. Yeah.
Okay, so that leads me to believe that the implementation of the stores A's and the store A pluses are wrong. We are doing only store A and store A plus, right? Are we doing store A actually? Oh, even better, we're not
Uh,
doing store A. Okay, so we can just go to VM plus store A plus. So what is wrong with this implementation? We go to the data stack, we pop something from there,
we pop the
then
value.
then we grab the value that is on the register A. We go to the RAM, we go to the index that is saved on the value of the A register, and we put the value that we picked from the data stack. Moreover, we go to the register A and increment its value. I have no recall if this is what we are supposed to be doing here.
It doesn't look to be wrong. It's just somehow it seems like.
Oh, remember something. The register A starts with value 0.
But the first thing we do is we fetch the literal and we push it to the register A.
Is this a load A or a load A plus? It is a push
My
A actually. Push
it's a push A.
push A. We see if we have the hardware of A. Then we grab the value of A and push to the data stack. So we are pushing 0.
Wait. Wait a second.
Don't you mean to do the opposite, like pop the data stack and push that into the value of A?
Oh, it's push the value from A, not to A. That's backwards then.
Okay. So my understanding is that you want something like value, and then we do something like self data stack.
No, what I meant is that the instructions in the programs are wrong. Um we should do pop A instead of push A, and that's that's the pop A. There's another push A that needs to change after that literal, yes. And that's it. Try to run the codes one more time. There we
For
go.
what? The result should be 30, no? That fixed some problems.
Uh,
The instruction addresses are now being maintained, so this is the same, which is correct. This is the same, which is correct. This is the same, and this is the same. it seems to me that the only things that we got wrong is the 8 and the 16. Because this is
Yeah,
14.
that is wrong actually. Okay,
So
so the first
what is
double
wrong
is
now? The
working.
load A plus, the plus.
Let me think for a second. We do a double, and then we do. Okay. We load A, we double it, so one becomes two. We dupe and store A plus. So we do have a two there. That's correct. Then we dupe the two again, double it, so now it's four, and store A plus. Oh, right. We start the four, but then we have a two below that. Is that what we want? I don't think so. The double and the dupe should be flipped, I think.
The dupe and the double. You mean these ones or
Yeah, these ones, the ones before the store A plus, they should be flipped. It should be double dupe instead of dupe double.
this one? And this one as well?
No, no, no. You wrote double double. It should be double dupe.
Oh, sorry,
Uh, we
sorry, sorry.
double we double the value, the numeric value, and then we duplicate it. So there's two copies of it.
Yes, we do
And
that
then the same,
twice.
we do that twice. Yeah, that one is backwards as well. And then it should be correct now. Try one more time.
And
How
boom.
funny is it that we actually found a bug in my program?
And now it is 30.
There we go. We found a bug in my program. So the first problem is that it was pop A instead of push A. I think the names of those instructions are a bit confusing. Um, so lesson learned. The second problem is I goofed and I should have done double dupe instead of dupe double. Yeah.
Okay, so I think that means, at least for the time being, that the parser is sufficiently extravagant to run
I
these programs.
mean, I mean, it's good enough to even find bugs in those programs, so I count that as a win.
Appreciate that. So I want to, yeah, I want to clean some things up. So I'm gonna put that there. Parser in as log. There, there.
Make a flag to print all the
Yeah,
stuff,
we
all
should
the
do a
bug
flag
mode.
for that for sure. Where is? Oh, these are errors. Okay, I think there's something like NS error, but I didn't went into it.
That's
Uh,
Apparently that's a class
Yeah,
constructor or a
probably
class
it's in
name.
class. Yeah.
and yeah, so this is our program. I actually like the RAM being at the bottom of the halting. I think that's okay. Uh,
Yeah, that's
okay,
okay for these small programs. It's good. It's not gonna be okay if we have a program that allocates a 4 kilobyte array or something.
I
Statically.
agree. So I'm gonna allow make that commented for now. So where are we doing that? Are we doing that here? Okay, so I think this is a good. This was great. We managed to find bugs in the programs. We also managed to check if the parser is sufficiently powerful to make those programs run, and we also identified the patterns, right? Which is what Zosing talks about all the time. We allowed the copy pasting to show us what we need to extract out. So now it's very
Yeah.
clear we should refactor as functions.
I'll make sure to make my own keywords file.
Yeah, yeah. Make your keywords, both of you true. So that will actually add a to do here. I'm actually don't know. I don't know where I'm gonna put this, but I'm gonna put in here.
Oh, well, we
Like
need to feed the program with a different set of keywords, right?
yeah. No, we need. It's not a transpiler, but I want a fancy word. We want translator between dialects. So you basically
Um,
give me a program, you give me the original dialect, and you give me the new dialect, and I'm gonna produce you a program equivalent with the new one.
Just
wait.
one
Oh man.
small nitpick. For the character you choose for the new variable syntax, less than and greater than are like convenient characters for operators,
I agree.
specifically for operator names. In particular, they are traditionally used to name the functions in forth that move values from the data stack to the return stack. And I think some dialects also use them to name the instructions that move values from the data stack to the registers.
Yeah, we can pick another symbol layer. That's completely fine. I'm gonna pick another one when I refactor this because now it's very clear what needs to go to become functions and so on. So we can just swap.
Yeah.
It's very easy. It's just swapping. Where it is? There. So just swapping this character. Maybe we should make macros out of these characters, actually. Like have all of them on the top, like Zosing style,
That seems reasonable, yeah.
and then we can just depend on them here. Yeah, that would be nice. Yeah. So now, uh, that was great. I'm very happy, man. I'm very happy that we managed to make that all of that work. Let's format all of the crap, and let's do a commit. Let's do a commit. Okay, so this is a very easy one. So number opcodes, add
Explicitly.
number to opcodes explicitly. Uh, okay. Validating instructions,
Oh, Nathan.
utilities, parser. Oh, there is an extra ns log that I didn't remove.
Question is it Nathan or Nathaniel? Think about this.
It's Nathan. We're both wrong
It is Nathan.
because that's the proper English pronunciation of
Oh,
his
but
name.
his name is I was just joking because I think his name is Nathaniel, right? Everyone is wrong.
Yeah.
So fix
Nathanael. Oh man, I
verb
was wrong. It looks more like Nathaniel, so I'll go with that.
again. Uh, update readme with new requirement. Update. I'm gonna actually rename this file later. Update Lemos keywords, but this is gonna be the default the keywords dot default. Keyword.
And out of all the languages to be popular, to be the lingua franca, it had to be English. I really am not amused with this idea.
And there. So
Uh,
update slash. I'm gonna say fix all as examples of programs.
Oh, by the way, we have a talk soon, right? Don't we?
We haven't what? Oh, the 24th, the 25th. Yeah, I'm gonna ask the guy at the end of this week if we are good. Good
Yeah,
to go.
ping Jean. Probably he will.
I'm not gonna push the compile flags, by the way,
Oh, I recommend you push because I. Oh no,
but
never mind.
it
It's
is
already on the
Nix
other file.
things.
Yeah, I'll just replace with my own leaks,
So
man. Yeah, not
update
it's that one.
parser implementation. Actually, it's more than that. It's finish
Do you know
initial,
Jean? By the way, Nathan. I think you don't know. He's a weirdo.
and it is
No,
there.
that's my friend. He's my Postgres friend. He
I'm
worked
gonna
at
finish the
BP.
recording now.
Okay.